Hi everyone, welcome to Algebra today on this lovely Friday. I'm sorry that I could not be here today. I am gone for my sister's wedding. So I'm still going to teach you this lesson, but this time over Screencast-O-Matic. So let's get started. Today's lesson is focusing on probability once again, and this is your last lesson of the year. Yay! So if you take a look, we're going to be focusing on independent versus dependent events today. And those are your big focuses. So if you take a look at this first slide here, it says Adam's teacher gives the two classes lists of titles and asks each student to choose two of them to read. Adam can choose one title from each list or two titles from the same list. And as you can see in this first one, you can choose one title from each list. So notice how the two lists are different. And then here, if you choose two titles from the same list, if you choose Animal Farm first, you can't choose that again, right? So the idea is that the total number of options changes. And this idea of the number of options changing from 5 to 4 and the number of options staying the same, do you see how this one, choosing Animal Farm, did not affect what you can choose in your second list? That's the idea of the difference between independent versus dependent. So if you take a look at the next few examples, that's kind of the theme that I want you to stick with is, does the total number of options change based on your situation or not? So we look at these first two examples here. It says, tell whether the set of events is independent or dependent. Explain your answer. Right? First, we're going to be looking at a standard deck of cards, and we're going to select one card, and I'm going to hold on to it. A friend selects another card from the same deck. So for me, I have 52 options. To choose my first card. But if I hold on to it, then my friend only has 51 options left. So that would mean that this is dependent. Excuse me. So in this case, your total changes. So I guess I should say total number of options. Okay? So next, if we flip a coin and it lands heads up, the first flip, there's two options, right? And then if we flip the same coin again, we still have two options. So in this case, since the number of options stayed the same, we have independent events. Okay? We can continue this process again with a couple more examples just for a good measure. If you take a look here, we're looking at a number cube this time, and it is showing an odd number. And then it's rolled a second time and showing a 6. Well, if we roll a number cube twice, we still have 6 options both times. It doesn't really matter what happens on your first roll or your second roll, as long as you still have the same number of options. Since these number of options are still the same, then this is going to be independent. This next one, if I choose one student from your class for a project, let's say that there's 25 students in a class. So first student, let's say there's about 25 options, or so. But if I take that first student away, I'm not going to choose that same student twice, right? So when I choose a second student, I only have 24 left to choose from. So this would be dependent. hopefully that makes sense. If not, you can kind of look up some of this stuff online on the Khan Academy videos that I've attached for you. Okay. Moving on. Now we're going to be calculating the probability. And then the idea is if you can determine something is independent, you can calculate this idea of two separate events happening at the same time. So the probability of A and B happening at the same time as two separate probabilities multiplied by each other. The probability of A times the probability of B. So please make sure that you get this equation down in your notes and that you specify that this is for independent events. And we're going to go through a few examples of this. Okay? So, moving on. Let's again get that equation down. A and B, two events at the same time, can multiply their individual probabilities if those two events are independent. So, this first example talks about we select a marble from a bag, we replace it, and then select another marble. So, this idea of replacing it means that we're putting that marble back, and then we're going to have the same number of marbles in our sample space. So this means that it's independent. All right, so let's get down to it. The bag contains 3 red marbles and 12 green marbles, which means there are 15 total marbles. What is the probability of selecting a red marble and then a green marble? So this is an AND probability that we select a red marble and the second time we select a green marble. We can calculate this according to that rule that we just wrote down as the probability of red times the probability of green. Well, what's the probability I choose a red marble? There's 3 red marbles out of the total of 15 marbles in the bag. So that was the first marble I choose, but I get to put it back, right? So I still am going to have a total of 15 when I go to choose the green one. And in this case, there's 12 green marbles. So if I'm calculating the probability of red and green, I'm just shortening this, I get something like, I'm going to reduce my fractions, so 1 out of 5 times 4 out of 5. Once again, that was reducing. So that way it's easier to multiply. 1 times 4 is 4, and 5 times 5 is 25. And then I end up with my probability. Let me slide this up so my face isn't in the way. Let's move on. Okay, so this time we're flipping 4 coins. I'm going to call heads just a capital H. In this case, it says, what is the probability of flipping 4 heads in a row? We're not changing the number of outcomes or the number of possible outcomes. So this is an independent case, so we can still use our probability formula. In this case, the probability of flipping heads the first time and heads the second time and heads the third time and heads the fourth time, we can calculate their individual probabilities and then just multiply them. This looks like a lot to write down, but it is important that you know what this notation means. Theoretically speaking, probability of flipping heads is 1/2. So I'm going to be multiplying 1/2 times 1/2 times 1/2 times 1/2. 1/2 times 1/2 is 1/4, 1/8, 1/16. For my final answer. All right. Just giving you guys another chance to finish writing this down. And let's move on to the next example. All right, we spin a spinner twice. The probability of spinning an odd number we spin it twice and we get two odd numbers, an odd and an odd. We can just multiply the probability of an odd number, which is 3 over 6, times the probability of an odd number, which is 3 over 6. I'm going to reduce these fractions.
Timer, if you can hear me, please let Mr. Anderson in the receiving area.
And then I'll find my final answer of 1/4. So notice how I just used a little shorthand. This is the probability of an odd the first time and an odd the second time. The reason we could use this rule is because the number of options did not change for our spinner. We still have 6 options either way. Okay. So let's move on to the next type of example, which is dependent events. Most of those examples involve repeating the same process with the same number of options. This idea now, if we were to think back to that marbles example, if we were to draw a marble out of that bag and not replace it, we're changing the number of options for whoever is drawing that second marble. So if you look here, originally there were, looks like 1, 2, 3, 4, 5, 6, 7, 8, 9 options. And if we took one away and did not put it back, now there's only 8 options left. This idea of without replacement means that there's 2 events that are dependent. And then you're going to have to be a little bit careful when you calculate those probabilities. You're going to have to change that total on the bottom. Okay? Once again, without replacement means dependent. So that's what we're looking for here. So moving on. The next few examples are going to be dependent. So in this case, we have a snack cart of 6 bags of pretzels and 10 bags of chips. If Grant selects a bag at random, which means he's taking one away, and then Iris selects a bag at random, that means Grant is not going to put this back. He's going to eat it, right? So this, it means he's not replacing it, or without replacement. Which means this is dependent. So now let's move on. What is the probability Grant will select a bag of pretzels and Iris selects chips? We're still going to use this idea of Grant selecting a pretzel times the probability of Iris selecting chips. But now this time, when I look at the probability Grant selects a pretzel, remember there are 6 bags of pretzels out of a total of 16 bags. So one of those bags is gone, so when it comes to be Iris's turn, there's only going to be 15 bags left for her to grab. And then the idea is how many of those are chips? That's what we're looking for here. There's 10 of them. So, per usual, I'm going to reduce my fractions just to make this a little bit easier on myself. So 3 out of 8 times, in this case, 10 over 15 can become 2/3. I get 3 times 2 is 6, 8 times 3 is 24, and that can be reduced to 1/4. Let me slide this up just that way you can see it. Once again, the key difference here is that the total changed at the bottom. There's no longer 16 bags for Iris to choose from. There are only 15. So you have to be careful when thinking about that stuff. All right, let's move on. So we can do a marbles example. There's a lot of different examples in here. In this case, we have 10 red, 12 white, 8 blue.